Hey everyone, and welcome to ILS Concepts for Electronics Technicians, Lesson 2, ILS Signals. In this lesson, we'll discuss amplitude modulation, 90 and 150 Hz, the CSB and SBO signals, and lastly, DDM and SDM. Since the ILS relies on the concept of amplitude modulation, or AM, we must first discuss the basics of an amplitude modulated signal. Modulation is the process of varying a transmitted carrier by the information we want to convey. The carrier wave is a sine wave at a fixed frequency. The information imposed on it is also a sine wave but at a lower frequency. It could be one frequency, many, or a variable frequency such as human voice. One important reason to modulate a carrier is that the transmit and receive antennas of that radio can be much shorter in length. Here we see an AM waveform in the time domain, much like the display of an oscilloscope. The information is outlined by the red lines. Notice that it appears in both the upper and lower sides of the carrier, known as the sidebands. The amount of modulation, known as the depth of modulation, can be calculated with the following formula. Let's focus on the upper sideband envelope using the maximum and minimum values to determine the modulation index. For this waveform, we could determine the modulation index is 0.5. To express this as a percentage, just multiply by 100 to obtain 50%. In this example, we again take the maximum and minimum voltage levels of the upper sideband envelope to determine the modulation index is 0.25 or 25%. This is just one method for determining the modulation index and percentage. In the case of M equals 0.1 or 10% modulation depth, we can see that the envelope doesn't stray very far from the carrier. As the modulation index increases to 0.9 or 90% modulation depth, we have a very deep minimum and maximum. Note, information is lost when the modulation index is greater than 1 or more than 100%. This is called over-modulation. Here we see an AM signal in the frequency domain, much like the display of a spectrum analyzer. The carrier is in the center with the greatest amplitude. In this example, we'll modulate that carrier with a 1 kHz audio tone at 50%. This results in two sidebands that appear above and below the carrier frequency. The total bandwidth of this signal is twice the highest modulating frequency, or 2 kHz. Let's now discuss the AM signal in the ILS, beginning with the 40 available carrier frequencies. The frequency ranges for the localizer are 108.1 to 111.95 MHz, and for the glide slope they are 329.15 to 335 MHz. Note that the localizer and glide slope frequencies are paired, so an aircraft ILS receiver can quickly tune to both systems under the localizer frequency only. Some ILS test receivers can only be tuned using the localizer frequency for this reason. In the ILS, the signal information is the 90 Hz fly right, shown in blue, and the 150 Hz fly left frequency, shown in red, which will be added together to become the composite signal shown at the bottom. In this demonstration, we can see that the 150 Hz is fixed with the 90 Hz changing in phase. Note the composite signal in magenta at the out-of-phase condition known as -90 plus 150, and at the in-phase condition known as +90 plus 150. In the ILS, we use only two instances of these phase relationships. That is when 90 is precisely in phase or out of phase with 150. Anywhere in between will cause system errors, although this is a rare problem in modern ILS transmitters. Recall that when the 90 Hz and 150 Hz signals are added together in phase, the composite audio waveform results. This is then mixed with the carrier at several watts of RF power to produce the signal below, known as the carrier plus sideband, or CSB. For the SBO signal, the 90 Hz and 150 Hz signals are added together out of phase, resulting in the composite audio waveform. This is mixed with the carrier in such a way as to reduce the carrier level to the lowest practical level, resulting in all energy being contained in the sidebands. This is also known as DSBSC, or double sideband suppressed carrier. In ILS maintenance, we simply call it the SBO. Let's now look at a simplified transmitter block diagram to understand how the CSB and SBO signals are created. In this diagram, we have a low power oscillator generating the carrier frequency, two hybrid mixers, and two modulators for the 90 and 150 Hz. For CSB, the carrier leaves the low power oscillator and splits at hybrid mixer A, in phase to each modulator. After the audio tones are modulated onto the carrier, they arrive at hybrid mixer B. From its summing output, the carrier has combined with the 90 and 150 Hz in phase to pass through an amplifier before being sent to the antenna array. For SBO, the carrier leaves the low power oscillator and splits at hybrid mixer A, in phase to each modulator. After the audio tones are modulated onto the carrier, they arrive at hybrid mixer B. At the difference output, the carrier and 90 Hz are out of phase. Additional amplitude and phase adjustments can be made here before final amplification. Let's return for a moment to ILS signal analysis in the frequency domain. The 90 Hz and 150 Hz signals shown appear as upper or lower sidebands from the channel frequency with a bandwidth of just 300 Hz. However, many instrument landing systems use two identical signals called a coarse and a clearance, or dual frequency. Both use the same carrier and 90 and 150 Hz signals. However, the carrier is offset by plus 4 kHz for the coarse, while the clearance is offset by minus 4 kHz at a reduced power of 10 dB. Depending on where an aircraft is, an ILS receiver will receive both due to its wide bandwidth design, but only process the stronger of the two. This is called the capture effect and will be discussed in later lessons. For simplicity, the remaining lesson will consider a coarse transmitter only. As an ILS technician, there are two important terms you should know. They are DDM, or difference in depth of modulation, and SDM, or sum of depth of modulation. They are measured on a portable ILS receiver and are the resulting sum and difference modulation levels between the 90 Hz and 150 Hz frequencies in the CSB signal. At the transmitter CSB through line, it's most commonly set for 0.000 DDM as read on a PIR. Through effects of the localizer and glide slope antenna arrays in the far field, the difference in depth of modulation will change as you diverge from the center line or glide path, just like the coarse deviation indicator deflected in the previous lesson. Let's begin by discussing how DDM is shown and read on a PIR. DDM is shown as a modulation index as opposed to a percentage. It generally is read to 3 number places past the decimal, so a typical transmitter CSB reading of 0% DDM, which is an even balance between 90 Hz and 150 Hz, would be read as 0.000 or just 0 DDM. The leading 0 is recorded but often omitted when read aloud. Also, an important note is that 90 Hz is always considered negative and 150 Hz is considered positive. Here is an example of a reading of 2 in the 150. Notice the PIR also shows 150 as the predominating frequency next to the DDM value. Here's an example of a reading of 1 in the 90. Notice the reading is negative and shows the predominant frequency as 90 Hz. On some models of PIRs, the number of averages may be set too high, and a fourth number would appear as the least significant digit, and should be omitted from being recorded or read aloud. Some technicians prefer this setting while others do not. Just keep this in mind as this reading would be read as 1 in the 150, not 13 in the 150. Let's now discuss SDM as shown and read on a PIR. SDM measurements are expressed as a percentage and typically made at the transmitter only. SDM is the combined total of both 90 Hz and 150 Hz modulations. At the localizer, this is 40%. If the DDM was 0 DDM, this would result in 20% modulation each. And it's important to note that as DDM changes, the SDM does not. At the glide slope, SDM is adjusted for 80%. If the DDM was set for 0 DDM, then this would result in 40% modulation each. Let's now go to the localizer far field to discuss DDM further. To analyze the DDMs here, you will need to attach the appropriate antenna kit as shown. Measurements are made at established ground check points, which are typically 2,000 feet from the array for a 14-element antenna system. In this example, we have one in the 150 on centerline. In this example, at the left of runway centerline, we read 154 in the 90, on the 90 side, course edge. In this example, at the right of runway centerline, we read 156 in the 150, on the 150 Hz side, course edge. This concludes Lesson 2 of ILS Concepts. In the next lesson, we will discuss vector analysis and antenna pattern developments.